Here's a number that should terrify you. 5.5 days. That's how long we have right now, today, before a catastrophic collision in space becomes statistically inevitable if our satellite control systems fail. In 2018, that number was 164 days. We had over 5 months of safety buffer. Today, we're down to less than a week. And if SpaceX's latest proposal goes through, launching 1 million satellites for orbital AI data centers, that buffer could collapse to under 1 hour. 1 hour. We are literally building a house of cards in space, and the wind is picking up. Welcome to Mindcast. I'm Will, and today we're diving into one of the most consequential stories happening right now, one that's playing out 300 miles above our heads, largely invisible to the public eye. SpaceX and xAI have merged, creating a $1.25 trillion entity with a breathtaking ambition to launch 1 million satellites to create orbital data centers for AI processing. Not 1,000, not 10,000. 1 million satellites. This represents the collision between infinite digital ambition and finite physical reality, and what happens when that collision occurs in the vacuum of space could determine humanity's relationship with the cosmos for generations to come.
Over the next 20 minutes, I'll take you through 3 profound insights that will fundamentally change how you think about space, technology, and our planet's future. First, we'll explore the orbital revolution, why we're moving from the connectivity era to the compute era in space, and why the shift demands unprecedented scale. Second, we'll unpack physicist Sabine Hossenfelder's stark warning about Kessler syndrome and discover why we're much closer to orbital catastrophe than anyone realized. And third, we'll dive into what I call the chemical Kessler, a completely overlooked environmental disaster brewing in our atmosphere that could reverse decades of environmental progress. By the end, you'll understand the stakes of what may be the most important decision about space that humanity will make in our lifetimes.
Let's start with our first key insight, the orbital revolution. To understand why SpaceX wants to launch 1 million satellites, we need to grasp a fundamental shift happening in space infrastructure. For decades, we've been in what experts call the connectivity era. Satellites were essentially cosmic relay towers, beaming data back and forth to Earth. Think Starlink internet, GPS navigation, satellite TV. But now we're entering something completely different, the compute era, where the actual processing happens in orbit. The satellites themselves become the computers. But why would you want to do computation in space? The answer is surprisingly simple. Earth is running out of juice. As AI models scale toward what researchers call artificial superintelligence, the energy requirements are becoming astronomical, literally. These training clusters need gigawatt-scale power connections. That's the output of entire nuclear plants. They need massive amounts of water for cooling. We're talking about industrial-scale consumption that's creating water scarcity issues in communities from Arizona to Ireland. And they need enormous amounts of land, which creates regulatory friction and community pushback everywhere they try to build. Elon Musk has stated explicitly that global electricity demand for AI simply cannot be met with terrestrial solutions without imposing hardship on communities. So the solution? Move the computation to where the energy is unlimited and free. Space offers what Earth can't, 1,361 watts per square meter of unfiltered sunlight, available 24/7 if you're in the right orbit. No clouds, no night, no atmospheric absorption. And here's the kicker. Space offers a heat sink at 2.7 Kelvin, essentially absolute zero. You can cool your processors by simply radiating heat into the vacuum of space. No water required, no massive cooling towers, no environmental impact from waste heat. But there's a catch, and it's a massive one. To make this work, you need unprecedented scale.
Solar panels are less power-dense than nuclear reactors. Radiative cooling is less efficient than liquid cooling. So to match the processing power of a terrestrial data center, you need to spread out across enormous areas of space. This is why SpaceX isn't talking about thousands of satellites. They're talking about 1 million. Let me put this number in perspective because it's almost incomprehensible. The total mass of everything humanity has ever put in orbit, every satellite, every piece of space junk accumulated over 70 years of spaceflight, is roughly 11,500 to 16,000 tons. SpaceX's proposal calls for 1 million satellites, each weighing at least a ton when you factor in the compute hardware, radiation shielding, and massive radiator wings. That's 1 million metric tons, nearly 100 times more mass than currently exists in orbit. We're not adding to space, we're industrializing it.
This brings us to our second key insight, the House of Cards warning. Recently, physicist Sabine Hassenfelder released an analysis that should make everyone pause and pay attention. Based on cutting-edge research by scientists Thiel and Bowley, she's warning that we're much closer to something called Kessler syndrome than anyone realized. But what exactly is Kessler syndrome? Picture this. One satellite hits another, creating debris, which hits more satellites, creating more debris, until eventually the entire orbital environment becomes a shooting gallery of high-speed fragments traveling at 17,000 miles per hour. Space becomes unusable for generations. It's like a nuclear chain reaction but with metal and velocity instead of atoms. Here's what's terrifying about Hassenfelder's warning. We've already shifted from what researchers call passive stability to active stability in orbit. Back in 2018, before the massive Starlink deployment, space was mostly empty enough that even if every satellite lost power and went dark, a collision was statistically unlikely for 164 days. Safety was a function of the vastness of space itself. There was just so much room that things rarely ran into each other. Today, with about 9,500 Starlink satellites buzzing around up there, that safety buffer has collapsed to just 5.5 days. Some simulations show it could be as low as 2.8 days. Think about that. We went from having months of safety margin to having less than a week.
This is where the researchers introduced something brilliant and terrifying called the crash clock, collision realization and significant harm. This metric measures the expected time until a catastrophic collision occurs if active collision avoidance systems fail. Think of it as a countdown to disaster. Right now, every satellite in orbit is constantly calculating trajectories, talking to other satellites, and making tiny adjustments to avoid collisions. It's like an intricate ballet performed at 17,000 miles per hour with thousands of dancers who never actually see each other. But what happens if that system breaks down? What if a solar storm scrambles the communications? What if there's a cyber attack? What if there's just a software bug? That's what the crash clock measures, how long until the music stops and the dancers start colliding.
Now here's where SpaceX's million-satellite proposal becomes truly chilling. The number of potential collisions scales geometrically with the square of the number of objects. Going from 10,000 to 1 million satellites doesn't just increase collision risks by 100 times, it increases them by roughly 10,000 times. The crash clock could drop from days to minutes, potentially under 1 hour. Think about what that means. The time required to detect a problem, calculate a solution, and execute a maneuver would exceed the expected time until the first collision occurs. The safety buffer would effectively cease to exist. We'd be living on borrowed time, measured in minutes, not months. But here's where it gets even more dangerous: solar weather. Coronal mass ejections and geomagnetic storms can heat Earth's atmosphere, causing it to expand dramatically. This increases atmospheric density at satellite altitudes, creating unpredictable drag forces that throw off orbit calculations. We saw this action in February 2022, when a relatively minor geomagnetic storm caused 40 newly launched Starlink satellites to fall out of orbit. That was during a quiet solar period. During a major solar storm, like the Carrington event of 1859, orbit prediction models fail completely because atmospheric density becomes chaotic. Satellites' positions become uncertain within hours, expanding from meters to kilometers of uncertainty. If your crash clock is under 1 hour and a solar storm scrambles your collision avoidance systems for days, the math is simple and terrifying. Kessler syndrome becomes a statistical certainty. This brings us to our third key insight, and this one's been almost completely overlooked in the public discourse: the chemical Kessler syndrome. While everyone's focused on collision risks in space, we're ignoring what happens when these satellites inevitably come back down. And here's something most people don't realize. Modern satellites, including Starlink, are made primarily of aluminum. When they burn up during re-entry, that aluminum doesn't just disappear. It converts into aluminum oxide nanoparticles that get injected directly into our stratosphere. We're talking about accidentally geoengineering our atmosphere on an industrial scale. Let me give you the numbers, because they're absolutely staggering. Currently, satellite re-entries deposit about 17 metric tons of aluminum oxide into our atmosphere annually. Previous studies of planned mega-constellations projected this might rise to 360 tons per year, already a 646% increase over natural levels. But SpaceX's proposal completely shatters these projections. To maintain 1 million satellite constellation with a typical 5-year lifespan, they'd need to launch and deorbit 200,000 satellites every year. At 1 ton each, that's 200,000 metric tons of aluminum burning up annually, generating approximately 24,000 tons of aluminum oxide. That's not a 646% increase, that's a 1,000 times increase over current levels. We're talking about injecting more aluminum into the stratosphere in 1 year than has occurred naturally in human history.
Why does this matter? Because aluminum oxide nanoparticles aren't just harmless dust. They act as catalysts for ozone destruction. They facilitate the conversion of benign chlorine compounds into reactive radicals that destroy ozone molecules. It's the same mechanism that creates the Antarctic ozone hole, but instead of being driven by polar stratospheric clouds in one region, this would be driven by industrial particulates globally. We could be looking at reversing decades of ozone recovery achieved by the Montreal Protocol, increasing UV radiation exposure worldwide, and potentially altering Earth's climate in unpredictable ways. The irony is profound. In trying to solve AI's energy problem by moving to space, we could end up damaging the very atmosphere that protects us.
Now, you might be thinking, surely SpaceX has considered this. They must have a plan. And they do mention one in their FCC filing: heliocentric disposal, essentially shooting satellites into orbits around the sun instead of burning them up in our atmosphere. Sounds clean, right? But when you run the physics, it's a fantasy. Moving a satellite from low Earth orbit to solar escape velocity requires about 3.4 kilometers per second of velocity change. Compare that to atmospheric re-entry, which needs only 0.15 kilometers per second. We're talking about 20 to 30 times more energy. Plus, using electric propulsion, this process takes months, during which each satellite becomes a slow-moving hazard crossing through every orbital zone between Earth and solar escape. Disposing of 200,000 satellites per year via heliocentric escape would turn the entire near-Earth environment into what researchers call a debris firing range. It's physically and economically impractical for mass disposal. The overwhelming majority of these million satellites will inevitably burn up in our atmosphere, making the chemical Kessler scenario not just possible, but inevitable. We're essentially proposing to conduct the largest uncontrolled atmospheric experiment in human history with zero oversight and no way to reverse course once we start.
So let me synthesize all this into 3 concrete takeaways that should concern every person on this planet. First, we're witnessing the transition of space from a global commons to a private industrial zone.
SpaceX's proposal effectively represents the enclosure of low Earth orbit. The most valuable altitudes and frequency bands are being claimed by a single entity, potentially excluding other actors, including entire nations, from accessing space for generations. This isn't just about internet or AI, it's about who controls humanity's gateway to the cosmos. And here's the kicker. China has already filed for 200,000 satellites in response. We're seeing a classic tragedy of the commons scenario playing out in real time, where no actor has an incentive to show restraint. Second, we're about to conduct the largest uncontrolled atmospheric experiment in human history. Injecting 24,000 tons of aluminum oxide into our stratosphere annually isn't just environmental recklessness, it's accidental geoengineering. Unlike deliberate geoengineering proposals that at least consider reversal mechanisms, this is a one-way street. Once those particles are up there, they're going to stay for years, potentially decades, altering ozone chemistry and climate in ways we simply don't understand. We're essentially treating our atmosphere as a garbage dump for space industry waste, with consequences that could dwarf the ozone hole crisis of the 1980s. Third, and most crucially, we're approaching what systems theorists call a phase transition, a point where the fundamental nature of the orbital environment changes irreversibly. The shift from passive to active stability, the collapse of the crash clock, the geometric scaling of collision risks, these aren't gradual changes we can slowly adapt to. They're threshold effects. Cross the line, and there's no going back. We could be witnessing the moment when humanity accidentally locks itself out of meaningful space exploration for generations. The current regulatory framework is laughably inadequate for this challenge. The FCC's 5-year rule addresses orbital debris but ignores atmospheric pollution. There are no binding international laws limiting aluminum oxide injection or restricting satellite populations. Here's the deeper question this raises. What happens when infinite digital ambition meets finite physical reality? SpaceX's Orbital Data Centre proposal offers a logically sound solution to terrestrial energy crisis facing AI development. The engineering is impressive, the business logic is sound, and the technical execution is probably feasible. But it solves terrestrial constraints by exporting the burden to orbital and atmospheric environments that were never designed to handle industrial-scale exploitation. We're essentially proposing to treat near-Earth space and our upper atmosphere as consumable resources in service of computational ambitions that may be fundamentally unlimited. It's the ultimate externalization of costs. We get the benefits on Earth, while space and atmosphere bear the consequences. The window for preventing this is closing rapidly. Without radical breakthroughs in remediation technology or binding international frameworks to cap orbital populations, we're likely looking at the transition of near-Earth space from a global commons to what researchers are calling an industrial sacrifice zone. This validates the direst predictions of Kessler syndrome models and could lock humanity out of meaningful space exploration for potentially centuries. But here's the thing, this outcome isn't inevitable. So what can you do? First, understand that regulatory frameworks can be updated. International cooperation is possible. Alternative approaches to AI computation exist, from more efficient terrestrial infrastructure to fundamentally different computational architectures that don't require massive energy expenditure. But these alternatives require public awareness, political will, and sustained pressure on policymakers who currently have no idea this is even happening. Second, follow the research. Scientists like Sabine Hossenfelder, Thiel, and Bowley are doing crucial work quantifying these risks with rigorous analysis. Their voices need amplification beyond academic circles. The conversation around space industrialization is happening largely in technical journals and regulatory meetings, but the consequences affect every person on Earth.
Third, think about the precedent we're setting. If we allow space to become an unregulated industrial free-for-all now, reversing that trajectory later becomes exponentially more difficult. The decisions made in the next few years about orbital population limits, atmospheric pollution thresholds, and space governance frameworks will echo for generations. We have a brief window to get this right, and once that window closes, the physical and political realities may make course correction nearly impossible. The stakes here couldn't be higher. We're not just talking about satellite internet or faster AI processing. We're talking about humanity's long-term relationship with space, our ability to explore and utilize the cosmos, the health of our planet's atmosphere, and the precedent we set for how technological ambition interacts with physical limits.
The collision between infinite digital dreams and finite physical reality is happening right now, 300 miles above our heads, and most people don't even know it's occurring. The question we face is profound. Will we choose infinite digital ambition at the cost of our finite physical environment, or will we find a way to balance innovation with stewardship of the orbital and atmospheric commons that sustain us? The answer will define not just the next decade of technological development, but potentially the next century of human relationship with both our planet and the cosmos beyond it. That's Mindcast for today. I'm Will. If this analysis opened your eyes to something you hadn't considered before, share this episode. The future isn't predetermined, it's a choice we make together. Until next time, keep questioning, keep learning, and remember, the most important conversations are often the ones happening just outside our field of vision. Thanks for listening.